Have you ever watched a robot navigate a maze or an autonomous rover precisely position itself and wondered, how on earth does it actually know exactly how far it's traveled? It's a pretty fascinating problem when you think about it. I mean, a robot doesn't have eyes quite like ours, so it has to rely on this really clever combination of mechanics, raw electrical power, and some ingenious math just to figure out its place in the world. So, welcome to this explainer. Today we're basically going to act as robotics engineers. We are breaking down the exact hardware and software you need to give a robot the power to move, and more importantly, the intelligence to track that movement.
Actuators and wheel encoders, building a robot drive system. Let's get right into it.
Here is our roadmap for today. We'll start with making the robot move, then look at the brains and wiring, tracking movement with encoders, decoding the encoder math, upgrading to smart actuators, and we'll wrap it all up with a quick chapter review and quiz.
All right, Section 1, making the robot move, bridging the gap between code and power. Okay, before our robot can track where it is, it obviously needs the muscle to actually move its body through space. And for this, we've got a very specific hardware shopping list. We're using two Pololu Metal Gear motors attached to wheels, and we are powering the whole thing with a hefty 12-volt battery. But the real magic happens right between our brain, which is the Tiva-C Launchpad microcontroller, and our muscle. Now, you might notice a little hiccup here. The Launchpad only outputs 3.3 volts, but our heavy-duty motor driver needs 5 volts to trigger. So what do? We drop in a logic level converter. It acts just like a translator, stepping up those tiny 3.3-volt command signals into robust 5-volt signals that the motor driver can actually work with. Absolutely crucial step. Once we've got all that hardware put together, how do we actually steer the thing? Well, our robot uses a really neat concept called a differential drive mechanism. If you've ever rowed a boat, you already understand this perfectly. Think about it. If you row both oars forward, the boat goes forward. But if you row the left oar faster than the right one, the boat turns to the right. Our robot literally does the exact same thing with its two side-mounted wheels. By independently changing the speed and direction of each wheel, we can navigate super tight corners without needing any complex steering wheels or axles. It's elegant and simple.
And to control those motors, we rely on this, the H-bridge truth table. An H-bridge is essentially the circuit inside our motor driver. Look at the inputs here, INA and INB. These are your digital logic pins. If INA gets a 1 and INB gets a 0, the motor spins clockwise. If we flip them around to a 0 and a 1, boom, it spins counterclockwise. If they're both 0, the motor hits the brakes. So by simply flipping these digital logic states and sending a separate PWM, or pulse width modulation signal to control the actual speed, we have total, precise mastery over our differential drive.
Section 2. The brains and wiring. Translating logic into hardware action.
So we've got our muscle completely set up. But, as we know, a muscle is pretty useless without a brain telling it what to do. For the Launchpad, we're writing our code using an incredibly approachable software environment called the Energia IDE. It uses a straightforward language called wiring. Setting it up is honestly a breeze. You just download the software, select the Launchpad Tiva-C from your board's menu, and make sure your computer has the right USB permissions. From there, you're literally just writing commands to set your motor pins to high or low to control the direction, and then using the analog write command to send that PWM speed signal. Hit upload and your robot springs to life.
Moving on to Section 3, tracking movement with encoders, giving our robot a sense of distance.
Okay, so the robot is moving. Awesome. But how does it actually know how far it's gone? This is exactly where we have to add senses to our robotic anatomy. To sense movement, we use a brilliant little piece of tech attached to the back of our motor called a Quadrature encoder. This sensor has two channels, channel A and channel B. As the motor spins, these channels generate digital square waves, which is basically just a fancy way of saying alternating pulses of highs and lows. But here's the kicker. Because the sensors are slightly offset from each other, there's a 90-degree phase shift between them. Why does that matter? Well, if the motor spins clockwise, channel A's wave will lead channel B. But if it spins counterclockwise, channel B leads channel A. So just by looking at which wave arrives first, our robot instantly knows which direction it's rolling. Pretty smart, right?
And that brings us to a really crucial number, 8400. Let me explain where that comes from. The encoder itself measures 64 counts per revolution, or CPR. But our motor has a gear reduction box on it to give it more torque, and we are also using a super clever programming trick called a 4x decoding scheme. By counting every single rising and falling edge of both channel A and channel B, we literally quadruple our resolution. When you multiply that by the gearbox ratio, it yields exactly 8,400 counts for just one single revolution of the final wheel shaft. That means our robot can sense a movement as tiny as a fraction of a single degree.
Section 4. Decoding the encoder math. translating pulses into positions.
Now, having 8,400 ticks of data per revolution is absolutely amazing for precision, but it also means our poor microcontroller is getting blasted with rapid-fire sensor data. To translate those pulses into actual usable positions, we use the 2-bit gray code pattern. A gray code is a very specific way of ordering binary numbers so that adjacent numbers only differ by one single digit. Take a look at the table here. If we transition from state 00 to 10, notice how only one number changed? Because only one bit changes at a time, our microcontroller doesn't get confused by tiny electrical glitches. By simply comparing the previous state to the current state of pins A and B, the brain knows flawlessly whether to increment our wheel tick count by +1 or decrement it by -1.
So to actually pull this off in C++ code, we rely on two incredibly powerful programming concepts: interrupts and volatile memory. An interrupt, well, it literally interrupts the processor to say, hey, the wheel just ticked, drop everything you're doing and run this calculation right now. We use an interrupt service routine, or ISR, to catch every single rising edge of our encoder channels. Then we declare our counting variables as volatile. That's a keyword that forces the brain to store the count directly in its ultra-fast RAM rather than its standard CPU registers. This guarantees we never, ever miss a rapid wheel tick, even when that motor is spinning at absolute top speed.
Section 5. Upgrading to Smart Actuators. The ultimate robotic upgrade.
So up to this point, we've built an incredible custom drive system from scratch. But let's say you're in professional robotics. What happens when standard DC motors and all this manual wiring just aren't precise enough for your application? Because as we've seen, standard DC motors require external H-bridges, somewhat messy level shifters, and we have to manually write all the math to track them. Well, enter the Dynamixel actuator. These things are intelligent, all-in-one smart servos. You don't wire them individually. Instead, you daisy-chain them together on a single network bus. They have their own internal PID controllers to handle all that complex math perfectly, and they constantly feed live telemetry, like current torque, exact position, and even internal temperature straight back to your computer. It's a real game changer.
And controlling them, incredibly streamlined. Instead of messing with low-level C++ interrupts, you connect them via a USB to Dynamixel adapter and write simple Python scripts. By installing the PyDynamixel library, you literally just scan the bus for your servos, which are identified by an ID from 1 to 255. Once found, you write dynamic limits for speed and torque and just tell the servo what goal position to go to. The actuator itself handles all the complex driving and braking internally. It's just a massive leap forward in robotic capability.
All right, Section 6, Chapter Review and Quiz. Let's test your robotics knowledge.
We've covered a huge amount of ground today, all the way from basic battery power up to Python-controlled smart servos. So let's lock in what we've learned. Question 1. What is an H-bridge circuit and why is it essential? Think back to our motor driver. The H-bridge is that critical hardware circuit that allows a tiny, low-voltage microcontroller to safely control the high current direction and speed of a heavy DC motor without totally frying itself. It's the bridge that translates our digital ones and zeros into actual forward and backward voltage.
Question 2. What is a quadrature encoder and the 4x encoding scheme? Remember our senses. The encoder senses rotations using two distinct out-of-phase wave channels. And that 4x scheme is our clever decoding method that counts every single rising and falling edge of both of those channels. It essentially quadruples our precision so the robot knows exactly where it is down to a fraction of a degree.
Question 3. How do we calculate angular displacement from this encoder data? Now, we didn't explicitly show the formula on the slide earlier, but we did talk about counts. To find the actual angle, you simply take your current count value, divide it by the total counts per revolution, like our 8,400 number, and multiply that by 360 degrees. And there you go. That gives you your exact angle of rotation.
And our final question. What makes a Dynamixel actuator different from a standard DC motor? Well, as we just saw, standard motors are kind of dumb. They require external brains and math to work. Dynamixels, on the other hand, are smart. They have built-in controllers, daisy-chain networking, and they feed back vital data like temperature and torque in real time.
You've mastered the hardware, you completely understand the logic, and you've seen the sheer power of tracking a robot's precise movements in the physical world. So with the muscle, the senses, and the brains all wired up and working perfectly together, what kind of intelligent robot are you going to build next? Think about it, and definitely keep exploring. Thanks so much for joining me on this explainer, and I'll catch you next time as we continue unpacking the amazing world of robotics.